As I said, project learnings fall into a few broad categories: technical, business, and programmatics. In my experience, most of those have both positive and negative trade-offs, and some of the benefits in one category cause issues in another category. As part of this project, one of the goals of the project was to identify gaps. What are the gaps in the services from the commercial cloud providers that are a hindrance to researchers using the cloud? But often, from what I've seen, a lot of those gaps are also part of that trade-off equation. In terms of technical learnings, if people want to delve into these a little further in the panel session after this, I'd be happy to. But clearly, as has been demonstrated by the last couple of presentations, cloud can be used for very complex large-scale simulations. But I would also add that we noticed in phase one that not all configurations are useful for HPC-style workflows. We did see a couple of the projects run into issues. For example, the Purdue group running WRF found that it worked fine up to about, I think they were running on 80 core nodes, and they were running up to about 4 nodes. Their simulations would get faster, but at a certain level, the internode latency broke down, and WRF didn't get any faster. And so things like placement groups, etc., may have helped there, but clearly WRF was working better on HPC, on-campus HPC clusters than would happen in the cloud. We also saw 1 or 2 performance issues with the SDSC group that they could not diagnose, again, because perhaps they didn't have access to the underlying compute infrastructure. One of the things that we did learn, there is optimized compute with things like placement groups and bulk API for reduced latency, but of course placement groups, etc., can attract extra costs, and using on-demand instances rather than spot instances also keeps costs up. Then again, using spot instances reduced cost, but could increase some latency. It meant that the code had to have checkpoints and be fault tolerant. We also note that large scalability requires proper elasticity and cost management. There's a fair bit of work that's gone into the work of all of the teams actually, in not only making sure that there's proper orchestration and teardown of services, but they're also tagged appropriately for cost management. Large scalability also requires institutional backing and negotiation on restrictions. We saw that on a number of cases with the, for example, the IceCube group, where they did the 51,000 GPU project. They noted that in order to actually get access to any large-scale resources, they needed to have an institutional backed contract with the cloud providers before the cloud providers would actually release the resources that they were looking for and change their default quotas. They also sort of indicated that it took not just the availability of an institutional contract, but really for them to get access to very large-scale resources took what they called a little bit of social engineering. They had to build a bit of excitement in their projects to get the buy-in from the cloud providers to be able to get those restrictions raised. We noticed from the SDSC project, for example, the convenience of the orchestration and the platforms that were made available through the cloud system also meant that they didn't actually get to tweak some of the finer details on the CPUs and the hardware, such as hyperthreading, etc. And that led to some difficulties in diagnosing performance problems. In fact, they weren't actually able to solve those problems even with the help of Amazon. New features and hardware offer performance improvement, but I think as Salva said at the end of his presentation, often that means you're working with technologies that even the cloud providers themselves don't have a lot of knowledge on and are learning along the way, because they've just been deployed and documentation is fairly sparse, and the researchers are learning as they go along with the cloud providers a little. Also, another technical learning is that data movement costs may need to be considered in some cases, although generally ingress costs are free with cloud providers, and egress costs do have waivers if connected through internet too. The way that people actually use the cloud is changing a little, and often the data ingest is through a load balancer, or institutions are using things such as Transit Gateway to manage the multiple virtual networks. And there's then can be costs of moving data, not only in and out of cloud providers, but also regions and between regions. Performance versus complexity. I just threw this little slide in just to this is just the number of new instance releases that Amazon released during the time that the E-CAS project was active. So from April 2019 to August 2021, as you can see, there's a very large number of new instance types that were made available. And there's all sorts of complexity in understanding what each of the new instance types means and what they are. Hidden within that is things like node density going up from about 64 cores to about 455 cores per node in some of the large instances now. Things like the attached GPUs. I think the NVIDIA V100 was released just around the start of the E-CAS project, and now most of the cloud providers are providing the NVIDIA A100 in clusters of up to 32 GPUs, etc. So those things change over time, and it'll be interesting to see whether that rate means that it's one of the questions I have really is does that mean that to keep up with the newer GPUs, really cloud is the way to go rather than physically installing them. Other technical benefits: scaling for large workloads. Once quotas, latencies and variances are overcome, elastic orchestration and cleanup can be automated. So tools such as Terraform that a number of the projects use make that really quite easy and able to quickly substitute instance types and things like that. There is definitely a rapid release of new hardware, as mentioned, can be a positive for access to new GPUs, etc., and decent quantities of newer GPUs. And the cloud, of course, is being built for ever more complex microservices, and they are building, for example, machine learning as a service and high-speed training as a service on cloud platforms in the commercial space now. Of course, there's high availability and reliability, and cloud is always good for community contributions and access. Trade-offs, of course, have been complexity of choice, the skills and experience of staff, abstraction from hardware, and cost prediction and management. Some of the business learnings along the way. Commercial cloud is a commercial relationship. It's a complex ecosystem of dealing with individual stakeholders, from funding agencies, legal, business, etc. and every institution handles this in a different way. One of the things that we did notice, particularly the difference between phase 1 of E-CAS and phase 2, is that in phase 1 of E-CAS, institutions were not particularly involved and particularly paying close attention to exactly how the accounts were set up within their organisation. But of course, once there was $500,000 per sub-award or more available, then institutions took a much closer look at where the money flows and how that would work. And so, for example, I think MIT and SUNY treated it almost exactly the opposite way. MIT wanted to make sure that the money flow was brought in through central IT and negotiated a new contract to make sure that came through central IT. SUNY, in their case, wanted to make sure that the money flowed through the SUNY Research Foundation. And so one was essentially an inhale and one was essentially an exhale. But it also gave an opportunity, because there was significant funding available. The SUNY group initially and then the MIT group were able to negotiate bonus credits because they were in a position to provide a contract which had a committed spend level. Another business learning was that project complexity and microcharging increase price complexity, which in turn makes cost estimation and value calculation a little bit more difficult. It probably should be also noticed that that some of the business processes that went with the change of contracting caused extra work for both of the main teams because it meant that new accounts had to be used. So a lot of the scripts that were set up using particular account codes and particular identifiers had to be recreated for the new setup scripts and new operations. Some of the programmatic improvements that I would recommend or observed and had recommended to me by the participants, I think it's fair to say that all teams would have preferred more funding for staff and or postgrad support. There was quite an amount of money, particularly available in phase 2 for compute, but the level allocated for staffing was relatively small. I think the comment that for phase 1, the 100,000 worth of credits was about right for phase 1 for the development phase, but the one postgrad or the approximately one postgrad worth of subsidy was perhaps not enough. The teams that are working on projects such as this are much bigger, and there's some people that need to do technical work and some people that need to do scientific work, and there's some improvements could be made there. While indirect charges were payable on cloud spend, they were fairly insignificant in phase 1. In phase 2, the indirect charges on the cloud spend were significant. So as well as the 500,000 that was available for cloud spend, the institutions received up to about 300,000 extra in indirect charges. But of course, that doesn't necessarily go directly to the research teams. So one of the potential recommendations were around limiting the level of the indirect charges, but allowing for greater staff support. It was also recommended that with the two-phased approach, one of the big problems was that at the end of phase 1, was somewhat abrupt, and there was a gap between phase 1 and phase 2. I think those teams that continued through to phase 2 would have liked to have seen some continuation of resources and continuation of staff funding between the phases, and those who weren't funded would have liked to have seen some continuity of funds to allow for wind down or migration of their projects to other platforms, etc. Also, the nature of how we went about the relatively fast startup of E-CAS meant that we put out a request for proposals with a relatively short 2-month time frame over December, January in 2018. There was a bit of an expectation that the projects would be already pretty much underway, shovel ready as I'd call it, and it led to the fact that all but one of the proposals were for R1 universities. And if we wanted to encourage cloud-based research from other universities, we might want to change the timing and the application process. And the other thing is that perhaps some shared resources and or paid research support from the cloud providers would help. While the cloud providers definitely helped in providing credits up front, and some institutions had good support contracts directly, and others had good connections with their sales channels. Perhaps a little more input from the cloud providers could have helped. We also ran a survey towards the end of E-CAS, and I've just selected a couple of results out of this just to highlight what were regarded as some of the main opportunities and benefits of cloud research. We sent this to mostly the CIO community, the CIOs of organisations connected to Internet 2, and had them distribute it within their organisations to answer. Probably not surprisingly, the results came back with the main opportunities and benefits were scale, ability to do large simulations, ability to use pre-built models and functions with relatively little technical knowledge, and fast access to new hardware. Things like it's easier than going through merit allocation, etc., weren't really significant, and long run times were actually not as significant as perhaps was observed by a couple of people in this project. In terms of what the main difficulties were, I think this also to some degree reflects the E-CAS project. Lack of research-specific training for cloud support, spend control and fear of overspend were fairly high. Not enough budgets, need more credit overall were fairly high. Getting the right level of support from cloud providers was an interesting one as well. And then time spent recoding, re-architecting, and lack of documentation and training materials for new features. Some of those came out within the project itself as well. And in conclusion, commercial cloud is no longer a simple proof of pool of virtual resources for hire. It's really a complex ecosystem. The range of hardware and services available is both a benefit, but a difficulty through the complexity that it adds and the fact that people need to try and keep up with things that are changing. Documentation and support can be difficult, particularly for the new features, but is often extremely good for people to get started. So I've had it commented that while new features might be lacking, it's often very easy for the general researcher to get onto cloud, and often easier than getting started in-house. It's quite clear that technical skills, there needs to be a team. All of the projects in E-CAS had a fairly large team working there, and the mix of technical skills, scientific skills, and that fostering a continuous DevOps and infrastructure as code culture really will aid in success of cloud. And finally, skilled staff are required to make use of cloud resources and cloud funds. And if you don't have sufficient skilled staffing, you won't be able to properly exploit the cloud funds. So that's a bit of a summary from my point in terms of where we're some of the learnings that we had from the project overall. I'd be interested in whether any of those who are actually participants in the project have any comments on that, or would like to expand on any of those. Otherwise, we might go to a few questions. Phil, Salva, in particular, do you think
a fantastic summary, Jamie? I actually, when you were reading some of those, I thought, oh yeah, this also happened to me, and I forgot to mention it. So I thought it covered everything fantastically.
Yeah, same here. I actually, you covered basically all of the big points that I was thinking about.
Yeah, we also did come up with, I do have a very long list of a lot of really minor points that, difficulties that the groups ran into, but I tried to keep it at a fairly high level. But Anna, do you want to, I believe we've got some more general questions. Do you want to take us through those? I don't know whether you want to direct them to people or perhaps ask them in general, and happy for Howard to jump in and answer some of those questions as well.
Thanks, Jamie, and thank you for that great summary. So, and thank you everybody for sharing in, the capture that Jamie just said, just share with all of us. But I do want to ask, so do you have any comments, or were there additional things or findings that, was anything missing in the summary?
I had one.
Oh.
Which was, the core intent of E-CAS is to, explore the viability of using commercial clouds for large scale scientific workflows. And I guess I'd ask the other panelists, do we think that we achieved that aim, that we demonstrated the viability? Salvador, go.
Sorry, the question was if you have demonstrated the viability?
Yeah.
So, all right. I mean, I think the simple answer is yes, right? And let me give you a slightly longer answer, is that, the cloud credits are going to end soon. And I've been frantically trying to come up with a way to get more cloud credits because this is so useful. I have a solution, but I won't say anything. You'll see an announcement on Monday, but suffice it to say that. But it actually, certainly there were things that we could do in the cloud that I thought that we just could not do with our existing resources. I would say that the existing resources have gotten a lot better, especially in the past 2 years. But I would say that there's some things that, like, I'm very worried that if we get rid of these cloud credits, we just won't be able to do these studies. And it's honestly, it's not, I mean, we planned kind of big spending studies, but it wasn't those that I was concerned about. It was actually all the parasitic stuff that we do to prepare. There was just so much flexibility. It was a lot of ease of use, and it was very easy to collaborate across institutes. And like that flexibility is hard to rival with the, existing like HPCs, the publicly funded stuff. And I mean, we use all of them, or we use a broad range of them, but the cloud I thought was, let's say, better. And I was quite nervous that we weren't going to have cloud credits. So in that sense, right, I can point explicitly to things that we could do that, we could not have done outside of the cloud. And I definitely think, the scientific impact will, I mean, we're starting to see it already, but it's going to be very large. That's my impression.
But just, oh, sorry, Salva, you want to?
Yeah, just to resonate with that answer, I think it was definitely achieved. But it's true that one of the sort of anxieties that one has is, what are we going to do when this finishes? And that's why we've been sort of frantically applying for other grants, and we got the ones from Human Brain Project and Exceed and so on, but they are obviously not the same. We've also got some research credits from Google themselves, which have this research program, but it's relatively small. So one of the things we are looking at is in future grants, both NSF and NIH include this as part of the budget. So resources on Google Cloud as part of the budget. And we've signed up for the Strides agreement to facilitate that with NIH. And I think it's really something that's going to be included by default in future grants.
Kevin, you had a hand raised.
Yeah, I don't know if you also want to hear from the rest of us, but I wanted to, if I could, emphasize
I do, please.
what I think both Phil and Salvador have implied about the funding aspect. So I think that we've definitely demonstrated at a technical level that we can use the cloud at really large scale for all sorts of scientific applications. And I think the next step is really the social and political economic implications of this. And for example, I've actually been reviewed negatively on other proposals for proposing to use funding for cloud resources for AI and other such things, because the impression in a lot of the scientific community and among the funding agencies is, oh, don't we already have all of these resources that are dedicated? Why do you need to go to the cloud? And we do have some resources. We don't necessarily have as many as people think we do. And the ease of use can often be a lot lower than in the cloud. You know, it's not like I just type in Google Cloud and click on a button and I get a machine. It's a lot harder than that often to get started. And so I think, you know, I don't think we're ever going to completely move away from dedicated resources for science, but there's a lot that we can learn from each other in terms of ease of use and how to scale things up. And in addition, hopefully we can socialize more the idea that these cloud resources should be considered a viable component of any scientific program. But this also means that on the cloud side, you know, we have to consider how we can get these resources with the limited funding that we do have for science, because of course we're always very constrained on that. So I think that's the thing we should keep in mind, you know, over the next 5 or 10 years, how to improve on those things.
Yeah, thank you for those comments. They're very insightful. I think one of the things when we were doing E-CAS that we were really focusing on was understanding what dimensions outside of just pure computational resources or storage resources the cloud brought to the table. And clearly, I think you've all articulated the flexibility, the ease of use, the collaboration, the access to, you know, the latest leading edge technology are part of, you know, instead of looking at it as cost as part of a value proposition, a value story. And so maybe that will certainly have some I think, great feedback to NSF and other agencies as learnings from E-CAS about why it could make a difference, and not just if you're just trying to do a straightforward, you know, how many cores of what type analysis. It's really what's the impact in getting the science done. And I think you've all done a fantastic job of not just articulating it, but actually demonstrating it. So thank you all for that.
All right. Unless there are any more thoughts on this first question, I have another one. All right. So approximately what, if you can estimate, so what percentage of your team's effort was spent in developing tools versus the scientific research stuff, including, you know, the experimentation, the literature search, all the writing you had to do on papers and so forth. So, you know, did using the cloud increase the tool building time, and did it accelerate your research in terms of publications and outputs? As one of my colleagues put, so is the reward worth the extra effort?
You want to go first, Salvo?
Go ahead.
All right. So this is, I mean, maybe it's a little tricky for me to answer because we basically, we wanted to build, we realized there were a bunch of tools we wanted to build, and we used this grant as an excuse to build the tools, right? Or maybe not an excuse, but a reason to build the tools, right? So I mean, in terms of, you know, what the research effort we wanted to devote to this project, it was for tool building, you know, to show the scientific impact of these tools, right? And so we saw the cloud as like the perfect lab for building and designing tools. We also know that, you know, as Kevin said, right, if we're gonna deploy this at scale, right, on a big scientific experiment, you know, no funding agency is gonna say, you know, you're gonna run this by default in the cloud, right? So the plan we always had was that we're going to use the cloud to build tools because we have, you know, access to state-of-the-art things that we wouldn't have at an HPC, and the HPCs, you know, frankly, aren't even configured in a way that we could even get this to work without a huge amount of effort, right? Much more than actually building tools in the cloud. So, I mean, suffice it to say, you know, that was like the focus of our project. In terms of like, you know, physics analysis and research that we got out of this for, there was actually quite a lot. And it kind of came as part of the research. I don't know how to say in terms of fractions, right? Because like all of us are doing physics research or, you know, scientific research. But, you know, in terms of our focus for this project, right, it was for building tools. I mean, in terms of, let's say, if I were to look at like, you know, my year of research, I would say, right, the tool building part was a major focus of our research in the past year. You know, mostly because you know, we're planning on trying to deploy this stuff, you know, as early as next year, right, in the systems, right? So some of the big scientific, you know, impacts we're only going to see in the next, you know, year or two, right? So for example, with the gravitational wave, you know, analysis stuff, we spent most of the year, let's say, I would say the first 9 months building the tools, and we spent the last 3 months, or let's say even 2 months, actually, you know, reaping the benefits of the tools. And, you know, and we're still actually building more tools because we realized, right, to deploy this, there's, you know, a few more things that we need to finish up and you know, get it ready for running. The big benefits we're going to see in a year, right, when, you know, LIGO turns on run 4 and our system is running, right, and you'll get alerts and you'll get analysis and all of this stuff. So it's a little hard to gauge, but I would say, you know, our use of the cloud here was for tool building. So, I mean, the majority of the work was done there.
No, I totally agree. Yeah, your research was tools. Salva, same question.
Yeah, yes, it's obviously quite hard to calculate the percentages, but our work in itself is always a large proportion of technical stuff and model developing. So that's part of what we do, whether we have access to these cloud resources or not. So I mean, very broadly, maybe it's 50-50, but we always have a lot of technical issues and effort that we have to put on the technical side because we do computational modeling. Of course, the moving to the Google Cloud required some extra effort to adapt our technologies to these new systems. But what I think it mainly did was accelerate them. So things that before we took 1 month, now we had in 1 day. So it basically put a lot of pressure on the personnel team to keep up. So we had lots of results, lots of things we could do, lots of models, lots of students, each doing their thing. And so we had to accelerate the science part as well. Not only the technical side to keep up with this, but the science to keep up with the technical output. So it was definitely worth it because, you know, we've advanced tremendously, but it was a big pressure on everyone to accomplish everything within this period of time.
Excellent. Thank you. Well,